In my previous lecture, I have explained how to handle missing data while doing clustering analysis. Second thing, I have explained how to find dissimilarity and similarity matrix. The third one, I have explained if there is a binary variable, how to find out the dissimilarity and similarity matrix. We will see how to handle other variables. For example, the agenda for this class is, if there is an interval scale variable, how to use that data set for the clustering analysis, and binary variable and how to use that data set for the clustering analysis we have done in our previous lecture. In this class, we will see if there is a categorical variable, how to use that data set for clustering analysis. Next, we will see if there is an ordinal variable, how to use for our clustering analysis, and if there are ratio scaled variables and how to do that data for our cluster analysis. And finally, if the data may be mixed type, the combination of these above data, in that case how to use that data set for our clustering analysis. The agenda for this lecture is how to handle the following data types. One is interval scale variable and binary variable that I have covered in my previous lectures. In this lecture, if the variable nature is categorical, ordinal, ratio and combination of above data set, that is mixed type, let us see how to see this kind of variables and how to use this kind of variables for our clustering analysis. First, we will take an example, categorical variable. A categorical variable is a generalization of binary variable, in that it can take on more than 2 states. It is similar to binary variable, but in binary variable only 2 options will be there, but in categorical variable there may be more than 2 states. For example, map color is a categorical variable that may have say 5 states: red, yellow, green, purple and blue. This is an example of categorical data set. Let the number of states of a categorical variable be capital M. The states can be denoted by letters, symbols or a set of integers such as 1, 2 up to m. Notice that such integers are just used for data handling and do not represent any specific ordering. The question which I am going to answer in this lecture is, how is dissimilarity computed between objects described by categorical variables? The dissimilarity between two objects I and j can be computed based on the ratio of mismatches. So, the formula to find out the dissimilarity for a categorical variable is d of I comma j equal to p minus m divided by p. You will notice that it is a small m. M is the number of matches, that is the number of variables for which I and j are in the same state, and the p is the total number of variables. Weights can be assigned to increase the effect of m or to assign greater weight to the matches in the variables having a larger number of states. So, we can give weightage also for different states. Now, we will take an example. With the help of example, I will explain how to find out the dissimilarity between categorical variables. So, the source for this example is this book, Finding Groups in Data, an Introduction to Cluster Analysis by Kaufman and Rousseau. The publisher is John Wiley. Suppose that we have the sample data as shown in the table. The table having 1, 2, 3, there are 4 columns. One is object identifier, second column is test 1 categorical data, third column is test 2 ordinal, the fourth one is test 3 ratio scaled. Let only the object identifier and the variable test 1 are available, which is a categorical data. So, for this example, we are going to consider only 2 columns. One is this object identifier, second one is the test 1, which is categorical data. The dissimilarity matrix is, see that we are showing only the lower triangle. There is a 1, 2, 3, 4 is the object identifier. The diagonal will be 0 because the dissimilarity is 0 for the same value of when I equal to j. So, this location is D21, second row first column. This location is third row first column, third row second column. This location is fourth row first column, fourth row second column and fourth row third column. Since here we have only one categorical variable, test 1, we set p equal to 1 in the equation, because p is the number of variables. So that dij evaluates 0 if the object I and j match, and 1 if the object differ. Thus we get 0, 1 0, 1 1 0, 0, 1 1 0. I will tell you how we got this matrix. Suppose let us find out how this location has come. This value is 1. The distance between, you see that this matrix D2 1. So D2 1 is, we will use this formula p minus m divided by small p. So p is number of variables, because here only one variable, minus m. When you compare 1 and 2, right, because the 2 comma 1 or 2 comma 1, see code A and code B, it is not matching. So the value of m is 0. So 1 minus 0 divided by p equal to 1, that is why we got this 1 value. Let us find out this value D41. So there is a one variable is this 4, another variable this. So we will use the same formula d of ij equal to, so p equal to 1. You see code A and for object identifier the code A is same for 1 and 4. So here the m is 1, so p also 1, m also 1, so this value is 0. This way the all other values were found. Now let us go to the next type of variable, ordinal variable. So ordinal variable is similar to categorical variable, but the order is more important. So in my, when I am explaining the previous data, that is a categorical variable, the one example is the pin code. For example, in India the pin code is an example for our categorical data. So that number is not representing any meaning. So now we will start with ordinal variables. A discrete ordinal variable resembles a categorical variable, except that m states of the ordinal values are ordered in a meaningful sequence. This term is very important, because there is a ranking, there is an order in each value. Ordinal variables are very useful for registering subjective assessment of qualities that cannot be measured objectively. For example, say very good, good, bad. So these are, we can give the rank 1, 2, 3. So here 1, 2, 3 says there is a rank for that. For example, professional ranks are often enumerated in a sequential order, such as assistant, associate and full professors. So the order is more important. A continuous ordinal variables look like a set of continuous data of an unknown scale, that is the relative ordering of the values is essential, but their actual magnitude is not. The problem with the ordinal scale is, in a class, suppose you are giving rank, those who are got 99 is the rank number 1. So those who are got number 2, 50 marks, rank number 2. You see that this 1 and 2 signifies the rank, but it is not the actual value, because this fellow got 99 marks, this fellow got 50 marks. So we are losing some important information when you go for ordinal data set, because for us this 1 and 2 is more important. How much mark they got, that is not important for us. For example, the relative ranking is a particular sport. For example, gold, silver, bronze is often more essential than the actual value of particular measures, because say there may be a different 3 scales. So rank 1, rank 2, rank 3. So this person gold, this fellow silver, this fellow bronze. Here what is more important is the rank is more important, not the actual measures. So ordinal variable may also be obtained from discretization of intervals quantities by splitting the value range into finite number classes. Sometime what will happen, if there is an interval scaled data set, that can be converted into ordinal variables. The values of ordinal variables can be mapped into ranks. So after converting ordinal, then we can bring different ranks. Let us see how to find out dissimilarity matrix for our ordinal data set. The treatment of ordinal variable is quite similar to that of interval scaled variables when computing the dissimilarity between objects. Suppose that f is a variable from a set of ordinal variables describing n objects. The dissimilarity computation with respect to f involves the following steps. The first one is the value of f for the ith object is xif and f has m of ordered states representing the ranking 1 to m. So, the m is the maximum number of rank, the xif is the that particular variable. So, what we have to do? We have to replace each xif by its corresponding rank RIF. So, RIF is the current rank. So, the MF is the maximum rank. Look at this data. This also we have seen our previous lecture. This is Euclidean distance. So, this is an example of dissimilarity computation. We have seen this previous table, that is the Euclidean distances. This is an example of interval scale data. From this interval scale data, we can convert this table into an ordinal data set. So, what we have to do? So, suppose the lowest distance is the highest rank. So, the lowest one is this one value. So, this can be ranked as 1. The second one is 5 point. So, this is rank 2. So, next one is 5.7 rank 3. So, and so on. For each variable, that is the interval data set, you can convert into ordinal data set by giving rank like 1, 2, 3 and so on. So, the highest value will have the highest rank. Standardization of ordinal variable. Since each ordinal variable can have a different number of states, it is often necessary to map the range of each variable onto 0 to 1 scale, so that each variable has equal weight. This can be achieved by replacing the rank RIF of the ith object in the fth variable by ZIF equal to RIF minus 1 divided by MF minus 1. So, the RIF represents the current rank, MF represents the maximum rank. Now, let us see how to find out the dissimilarity computation. The dissimilarity can be computed using any of the distance measures described by earlier, like that in the interval data. Now, let us take an ordinal data, then I will explain how to find out the dissimilarity matrix. Suppose that we have the sample data of the following table, the same table which I have seen. So, there are 4 columns: object identifier, test 1, categorical, test 2. Now, we are going to consider these 2 columns. One is object identifier, next one is test 2, that is ordinal data set. Suppose that we have the sample data set for the following table, except that this time only the object identifier and the continuous ordinal variable test 2 are available for us. There are 3 states of the test 2, namely good, excellent and fair. So, the MF is 3 because that is a maximum number of states. The step 1, if we replace each value of the test 2 by its rank, the 4 objects are assigned on the rank 3, 1, 2, 3 respectively. How is the 3, 1, 2, 3? So, this we are going to call it as 3, this is also 3, this is 1, this is 2. So, how we are ranking this variable? 1 is fair, 2 is good, 3 is excellent. That is why we got this one 3, 1 and 3, 1, 2 and 3. Step 2, normalize the ranking by mapping 1 to 0, rank 2 to 0.5, rank 3 to 1. How we got this one? Rank 1 equal to 0, because the RIF value is 1. So, 1 minus 1 divided by, there are the value of MF is 3. So, 0 minus 3 it is 0. The second one rank 2, 2 minus 1, 1 divided by 3 minus 2. So, what will happen? It is 1 divided by 2, it is a 0.5. The third one, so value of RF will be 3 minus 1 divided by this also 3 minus 1. So, it is 2 by 2, that is equal to 1. That is the way to standardize. Step 3, we can use say the Euclidean distance, which results the following dissimilarity matrix. So, this is our Euclidean distance. So, the first column, for example, it says the object identifier. This was our ranking ordinal data set. This is our standardized value. So, 3 is mapped into 2, 1. How we got this one? See, 3 equal to 1. So, 1 equal to 0, 2 equal to 0.5, 3 equal to 1. This is our standardized data. This is in the Z scale. This is our object identifier. This was our ordinal data. Now, let us see how this matrix has come. Suppose if you want to know the distance between object identifier 2 and 1. So, between 2 and 1 the distance is 1. So, root of 1 square is 1. So, let us see how to find out the distance between 3 and 1. So, 3 is 1. So, the formula is 1 minus 0.5, that is a 0.5 whole square. When you take square root, this is 0.5. Let us see 3 to 2. So, 3 to 2, 0 minus 0.5 whole square root, that value is a 0.5. Let us see 4 to 1. What is the distance? So, 4 to 1 is 1. This distance is 1, 1 minus 1. That whole square, you take square root, that also 0. Let us see how we got this 1. So, that is a 4 to 2. So, 4 to 2 is 1 square root, that value is 1. So, 4 to 3. So, this distance is 0.5 minus 1 whole square root, that value is 0.5. So, this is an Euclidean distance. This is our standardized Z value. Now, let us go to the next type of variable, that is a ratio scaled variable. A ratio scaled variable makes a positive measurement on a nonlinear scale such as exponential scale, approximately the following the formula: a e to the power bt or a e to the power minus bt, where an a and b are positive constant and t is typically representing the time. So, common example include the growth of a bacteria population or the decay of radioactive element. So, that is an example of ratio scale. Here the concept of ratio scale is there is a meaning for our absolute 0. When there is a absolute 0, you can do all kind of arithmetic operation using ratio scaled data. So, computing the dissimilarity between the objects. There are 3 methods to handle the ratio scaled variable for computing the dissimilarity between the objects. The first method is treat ratio scaled variable like interval scaled variables. This, however, is not usually a good choice, since it is likely that the scale may be distorted. But most of the marketing examples, we want to differentiate the ratio scale and interval scale. Even though we collect the interval scale, so we will use as a ratio scale for finding all kind of statistical tests. The second method is apply logarithmic transformation to a ratio scaled variable f having the value xif for a object I and using the formula yif equal to log of xif. It is nothing but if there is a ratio scale, just you take log of that. So, that can be used for further analysis for finding the dissimilarity matrix. The yf values can be treated as interval value. Notice that for some ratio scaled variables, so log of log or other transformation may be applied depending upon the variable's definition and the applications, because for we can use any kind of different transformations. The third method is treat xif as a continuous ordinal data and treat their rank as intervalled values. So, this is the third method. The latter 2 methods are the most effective, although the choice of method may depend upon the given application. Now, let us take an example of ratio scaled, then I will explain how to find out the dissimilarity matrix. This time we have the sample data of the following table except the only object identifier. So, we are going to consider this one and the ratio scaled variable, this column. So, we are going to consider only these 2 columns for finding the dissimilarity matrix. So, in the third column ratio scaled 445, 22, 164, 1210. Let us try a logarithmic transformation. So, just we are going to take the log of the column 3 values. Taking the log of test 3 results in the values become 2.65, 1.34, 2.21 and 3.08 for subject 1, 2, 4 respectively. When you look at this, after taking log transformation, the value it is compressed. See, that is scaled down. That is the purpose of scaling. So, instead of using 445, you can use 2.65, it is easy to handle. So, instead of using 22 for cluster analysis application, you can use 1.34. So, the benefit of taking log of this one is it is compressed in a smaller scale. So, using the Euclidean distance of the transformed values, we obtain the following dissimilarity matrix. So, this is our dissimilarity matrix. So, this is object identifier 1, 2, 3, 4, this is 1, 2, 3, 4. For example, D21, how we got this one? This is 1, this is 2. So, we have to find the difference. We have to use this formula 2.65 minus 1.35 whole square root, that value is 1.31. For example, 1 and 3, so this is 1 and 3. So, the difference is 2.65 minus 2.21 whole square, take square root. So, that will be this value. Then suppose 4 1, so this is the fourth one. So, find the difference 3.08 minus 2.65, take square root. So, that value is 4.3. The same way we can get the other cells. Now, we will enter to another type of variable. It is not another type of variable, where whenever we do the cluster analysis, there is a possibility of these variables like categorical, interval, binary may come together. So, that type of data types we are calling it is mixed types. So far, we have discussed how to compute the dissimilarity between objects described by variables of the same type, where these types may be either interval scaled, symmetric binary, asymmetric binary, categorical, ordinal or ratio scaled. However, in reality, in many real databases, objects are described by the mixture of variable types. So, whenever the mixture of these variable types are coming, how to use that data set, how to standardize that data set for our further analysis of our clustering analysis, that we will see now. In general, a database can contain all of 6 variable types listed above. So, how can we compute the dissimilarity between objects of mixed variable types? One approach is to group each kind of variables together, performing a separate cluster analysis for each variable type. This is feasible if these analyses derive compatible result. However, in real applications, it is unlikely that a separate cluster analysis per variable type will generate compatible result. So, we can group the same variables, then you can go for clustering analysis, but sometime that will not be compatible, we cannot follow that approaches. A more preferable approach is to process all variable types together, performing a single cluster analysis. So, in general what we have to do, we have to, by grouping all the variables, we have to do a single cluster analysis that will give you the meaningful result. One such technique combines the different variables into single dissimilarity matrix, bringing all of the meaningful variables onto a common scale of the interval 0 to 1. So, one way to bring all different types of variables into a common scale is nothing but converting all the variables and bringing into this scale, nothing but standardization, that is 0 to 1. Suppose that the data set contains p variables of mixed types. So, the dissimilarity d of I comma j between objects I and j is defined as d of I comma j equal to sigma of f equal to 1 to p. So, delta I j f d I j f divided by sigma of f equal to 1 to f delta I j for f, where the indicator delta I f equal to 0 if either xif or xjf is missing, that is there is no measurement of variables f for object I or object j, or xif equal to xif equal to 0, then ij equal to 0, or the variable f is symmetric binary. Otherwise, when the option is not there, then the delta if of f equal to 1. The contribution of variables f to the dissimilarity between I and j, that is dij f, is computed depending on its type. If f is interval based, so di of f equal to modulus of xif minus xjf divided by max h xhf minus minimum h xhf, where h runs overall non missing objects for variable f. If f is binary or categorical, so dij equal to 0 if xif equal to xjf, otherwise dij f equal to 1. If f is ordinal, compute the rank RIF and ZIF using this formula: ZIF equal to RIF minus 1 whole divided by MF minus 1, and treat ZIF as interval scaled. If f is ratio scaled, either perform logarithmic transformation and treat the transformed data as interval scaled, or treat f as a continuous ordinal data, compute RIF and ZIF, and then treat ZIF as a interval scaled. The above steps are identical to what we have already seen for each of the individual variable types. The only difference is for interval based variables, where here we normalize so that the values map to interval 0 to 1. Thus, the dissimilarity between objects can be computed even when the variables describing the objects are different types. The summary of this lecture is, I have explained how to handle the different types of variables. For example, if it is a categorical variable or ordinal variable and ratio scaled variable and variables of mixed type, how to find out the dissimilarity matrix. So, what I have done in this lecture, I have taken one example. In that, using that example, I have explained how to find out the dissimilarity matrix, but only for the last, that variables of mixed type, I have explained only the theory portions. In the next class, I will take another example which are mixed in nature, then I will tell you how to find out the dissimilarity matrix. Along with that, we will start a new topic in the next lecture, that is a k-means algorithm. Thank you very much.